In this video, we're going to learn about two subspaces which are associated to a given linear transformation. These subspaces somehow gives characterizations to the behavior of the given linear transformation. These subspaces are called the kernel and range of a linear transformation. Before we talk about the kernel and range of a linear transformation, we need to have the following definitions first. So here, if you have a function f from x to y, if S is a subset of X, we define the direct image of S under the function f as the set denoted by f bracket x containing all the images f of S where S is an element of capital S. In terms of pictures, if this represents your set X and this represents the set Y, S is a subset of X, like in this picture. We collect all the points S, little s in capital S, and then take it to an element in Y called as f of S. If you're going to collect all the images of the points that are found in this set, under the function f, that collection would be the direct image of S under F. On the other hand, if you now have a subset T of the set Y, we define the inverse image of T under F as the set denoted by this symbol, F inverse bracket T, to be the collection of all points in X whose images are found inside T. So in terms of Venn diagrams, if this is the set X and this is the set Y, you have, for example, a subset T. Let's change colors. For example, this is the subset T of Y, and you're going to look at the points in X. Now we're going to look at the points in X which are sent to an element inside T. If the image of X is found to be inside T, then the point X itself is inside the inverse image. In fact, the inverse image of T is precisely the collection of those points that are mapped to an element to T, or to an element of T. So in pictures, they are shown as follows. So this is the inverse image of T. To give you some example, suppose that X and Y are sets given as follows. So X contains 1, 2, 3, 4, 5, and Y contains 6, 7, and 8. Let F be the function from X to Y defined by the following diagram. So in this diagram, an arrow means an image, 1 is sent to 6, meaning to say f of 1 is 6. 2 was sent to 8, so meaning to say f of 2 is equal to 8, and so on. For example, if we consider the set S containing 1, 2, 4, as you can see, this set is a subset of X, right? This is a subset of X. The direct image of S can be obtained by simply taking the images of every point in this set. So in other words, the direct image of S can be calculated by simply performing or evaluating F at each of these points, and then listing down the images. For example, f of 1 is 6 as in the diagram, f of 2 is 8, and f of 4 is also 6. Therefore, the answer is the set containing 6 and 8. On the other hand, if T is the set containing 7 and 8, as you can see over here, this set is a subset of Y, I'm sorry. So when you want to know the inverse image of the set 7 and 8, you look for the elements in X which are mapped to either 7 or 8. So, if you look at the element 7 over here, and look at the things that are mapped to 7, in this case, only the element 3 was mapped to 7, therefore, 3 is part of the inverse image. Now, when you look at the element 8, there are precisely 2 elements in X which are mapped to 8, namely 2 and 5. Therefore, 2 and 5 are also elements of the inverse image. This means that every element of this set containing 3, 2, and 5 are mapped to an element of T which contains 7 and 8. Therefore, the inverse image of T is the set containing 2, 3, and 5. Take note that in this example, f is an arbitrary function on plane sets x and y. So in our discussion, functions are linear transformations between vector spaces. We have the following result. This result tells us that a linear transformation preserves the subspaces of the given vector spaces in the following manner. So, if L is a linear transformation from V to W, okay, over the field F, and if S is a subset of V and T is a subset of W, then S being a part of the domain, it has a direct image under L. The direct image under L will now be a subset of W. In fact, it's not just a subset, it is also a subspace of W. On the other hand, this subspace T of the arrival space W will have an inverse image which is a subspace of the domain V, or the departure space V. Simply saying, it says that the direct image of a subspace is also a subspace of the arrival space. And also, the inverse image of a subspace of the arrival space is a subspace of the departure space. So I'm going to prove this part, the part where T is a subspace of W, and I'm going to prove that its inverse image is a subspace of V. The other conclusion will be left as an exercise. So in this case, we will prove that the inverse image of T under L, which consists of all those V in the domain whose images are in T. I think there is typo error over here, so that should be T. Whenever T is a subspace of W. First of all, L of 0, we know that because L is a linear transformation, L of 0, V is equal to the 0 of W, which in the first place is an element of T because T is a subspace. Because 0 was mapped to 0W, therefore 0V is in the inverse image of T. We now check for the closure under addition. If now you have two elements V1 and V2 from the inverse image of T, then of course by definition of the inverse image, their images are elements of T. Now, if you look at the image of the sum V1 plus V2, because L is linear, it becomes L of V1 plus L of V2, which in turn is going to be an element of T because this is an element of T, this is an element of T, T is a subspace of W, therefore it is closed under addition. Because this sum was sent by L to an element in T, it follows that the sum V1 plus V2 is in the inverse image of T. Finally, we show closure for scalar multiplication. If V is an element of the inverse image and alpha is a scalar in F, then of course, by the definition of the inverse image, the image of L is going to be inside T. Thus, when I look at the image of alpha times V, because L is linear, it equals alpha times L of V. And because L of V is in T is a subspace of W, I know that the resulting scaled vector is also an element of T. Therefore, because this is a vector was sent to an element in T, it follows that the vector alpha V is in the inverse image of T. This completes the proof that the inverse image of T is going to be a subspace of V. We now have a corollary to this theorem. This corollary is in fact a particular case of the general theorem. Take note that V is actually a subspace of itself. So therefore, I can take the direct image of V, and I am sure that that direct image is a subspace of W. Also, I can consider the trivial subspace of W, in this case, the one containing only the zero vector. We know that this is a subspace of W. From the previous theorem, I know that its inverse image must be a subspace of V. But what are the elements of these subspaces? The elements of the subspace L bracket V contains all the images L of V where V is an element of capital V. It's a subspace of W. On the other hand, the inverse image of the trivial subspace of W is equal to all the set of all points V from V, capital V, whose images are sent here, therefore whose images are 0. In linear algebra, we give names to these subspaces because they are going to play an important role. So here, let L be a linear transformation. The range or image in elementary mathematics, I think the range is used more often. Okay, the range of the linear transformation L consists of all the images of all the points in the domain. So you take the images of all the points in the domain, you collect them in one set, that is called the image. Take note that in our in the previous corollary, this is the subspace L bracket V. On the other hand, the kernel of a linear transformation is the subspace denoted by this symbol, and it consists of all the vectors V in the domain which are mapped to the zero element of W, or to the zero vector of W. In the previous corollary, this set is precisely the inverse image of the trivial subspace of W. Okay, so simply saying, the range is simply the range of the function. But not every function in mathematics has a kernel, right? But in linear algebra, when you talk of linear transformation, it has a kernel because the sets that we relate under the linear transformations are vector spaces. In particular, vector spaces have zero vectors. That's why we can talk about the kernel. Remember that the kernel consists of all the elements in the domain which are mapped to the zero vector. Or in other words, I always say this, no? The elements of the kernel are the vectors from the domain which are trivialized by L. When I say trivialized by L, I mean L takes V to 0. So in other words, L annihilates the vector V, if you want to say it like that. In pictures, this is what is happening now. So this is the domain V. This is the arrival space W. If you take the image of all the points in the domain, you collect them in the arrival space. And if this is the collection of all the images, this is called as the image or the range of the linear transformation, denoted by this. Of course, the zero vector in L will be an element of the range because the range is a subspace of W. Now, if you now collect all the elements in V, which are trivialized by L, meaning to say, L kills the elements of the kernel of this kernel because it takes them to 0. That is what we call as the kernel of the linear transformation. In the case when the image and the kernel are finite dimensional, they have, of course, their corresponding dimensions, right? The dimension of the image, or the size, you can call it the size of the image, is called as the rank of L. The word rank was taken from the word range. On the other hand, the dimension of the kernel as a part of the domain is called as the nullity of L, because the nullity tells you the size of all the objects which are nullified by L. You can think of it that way. When you say nullified by L, L takes them to 0. We have the following remarks. If zeta denotes the zero transformation from V to W, now we know that what does the zero transformation actually do? The zero transformation sends everything in V to 0 in W. Alright? So in this case, it follows that the kernel of the function zeta is the entire V because everything in V is mapped to 0 of W. On the other hand, the image of, I think this is wrong once again. The image of zeta is now consists of only the 0 vector in W because everything is simply turned into the 0 vector. So I'm sorry for the mistake. The image of zeta is the trivial subspace of W because everything is just sent to 0, so the set of images consists of only 0. Okay, let me change this for you. Now, if you recall the identity operator, what does the identity operator do? The identity operator does nothing. So if you take V as an input, the output will be V as well. And this will happen for all V in V. So this is an example of a linear operator that does nothing on V, right? Whatever you input it, that is also the output. Hence, the set of all elements that are trivialized by the identity transformation is only the 0 vector of V because, of course, every linear transformation takes 0 to 0, therefore the 0 vector is an 0, 0 V is an element of the kernel always. But I know that no other elements could be in the kernel because if V is non-zero, because ID is the identity transformation, the image of V, if V is not 0, is also not 0, in fact, itself. On the other hand, because of this fact that the identity does nothing to V, the image will also be the entire V. Take note again, when we say operator, this is the transformation from V to itself. Let's now have a non-trivial example. So here, we are asked to find bases for the kernel and the range of the linear transformation from R3 to R2 given by the following function. So I think we have seen this example in the last video. Now we have shown that this is actually a linear transformation. So if you want to see, if you want to see the proof that L is actually linear, you could go back to the previous video. In this case, we're now going to find bases for the kernel and the range. Now, in linear algebra, when we want to describe the elements of a subspace, we normally give a basis to them because a basis determines everything in the space. So for the kernel, okay, so by definition, we are going to look at the elements in the domain, which is R3, which are mapped by, according to this rule, to the zero vector in R2. So in other words, in symbols, the kernel of L consists of all the vectors x, y, z from R3, which are mapped to the zero vector in R2. Meaning to say, the zero vector in R2 is the ordered pair 0, 0. But by definition of L, that is x minus y, x plus z equals 0, 0. Therefore, the point x, y, z is in the kernel of L if and only if x, y, and z satisfy this equation. Therefore, it must satisfy this linear system that x plus y is 0 and x plus z is also 0. So if you're going to solve this, we're going to solve this because we're looking for the kernel, right? We're going to apply the Gauss-Jordan algorithm. It gives us the following matrix: 1, 1, 1, 0, 0, 1, and then these are all 0. So these are the variables x, y, z in columns, right? So if we apply this elementary row operation, I get this one, negative 1, I think 1, 0. And then I multiply the second row by negative 1 because I need to have a pivot over there. Okay. Finally, I'm going to eliminate this one from here. So that's E, 1, 2, negative 1. That's going to be 1, 0, 1, 0, 0, 1, negative 1, 0. Okay. So in this case, what has happened over here? So in this case, xyz is in the kernel of L if and only if. So how does xyz look? So over here we know that x and y are leading variables, right? And z is free. So we could assign a variable, let's say r, for z. Looking at the first equation or the first row, x plus z is equal to 0, therefore x is minus z, so this is going to be minus r, right? For y, looking at the second row, y minus z is equal to 0, therefore y is equal to z, therefore y is r, where r is a real number. Take note that you can write this as r times minus 1, 1, 1. Therefore, every element in the kernel is precisely the set of all multiples of the vector minus 1, 1, 1. Therefore, the kernel of L is the span of the vector minus 1, 1, 1. So, a basis for the kernel is this singleton, because we know that a singleton containing one non-zero vector is always linearly independent. And because this is a spanning set for the kernel, therefore it's a basis for the kernel. Alright, so we now look at a basis, or we now look at the range of the function. But before that, let me erase this board. Okay, so here the kernel is spanned by this vector, therefore a basis for the kernel is this set. Okay, so we now look at the range. Now the range of L, by definition, is the set of all images, so like this, no? So that XYZ is in R3, or in other words, XYZ are real numbers. But as you can see, L of XYZ by definition is X minus Y, X plus Z. So that it becomes, you could also write this condition as follows, if you want. Okay. Now take note that the image X minus Y, X plus Z can also be written as follows. It can be written as X times 1, 1, because both coordinate has an X, plus Y times negative 1, 0, because this has minus Y, this has no Y, so that's 0, plus Z times 0, 1. Okay? So therefore, as you can see, every element in the range is nothing but a linear combination of these three vectors. Okay? Right? Right. So, therefore, we can say that the image of L is really the span of the vectors 1, 1, minus 1, 0, and 0, 1. But we know that the maximum dimension of the image is 2 because it is a subspace of R2. Therefore, we know that this set of vectors is linearly dependent. So in order to find a basis, we must eliminate the redundant vectors here. To eliminate the redundant vectors, we perform the following Gauss operation. We put these vectors in columns and then run the Gauss-Jordan algorithm like so. But as you can see, this is also the matrix that we have calculated the RREF a while ago, right? I notice that for this, only the first two columns, okay, after performing RREF, only the first two columns receive a pivot. Therefore, it means to say that the third column is a vector that is redundant, right? So we could just eliminate the third vector without the fear of eliminating a necessary vector. In fact, the one that we have deleted is going to be redundant only. So therefore, we can say that the image of L is now spanned by 1, 1, minus 1, 0. Therefore, a basis for the image is the set containing, no, of course there is no unique basis, right? Okay, but as you can see, the image is two-dimensional. It's a subspace of R2. Therefore, the image is actually the entire R2. Alright? So as you can see over here, the dimension of the kernel, or the nullity of L, because the kernel is generated by only one vector, the nullity is 1, and the rank of L is going to be 2 because it's two-dimensional. Okay, take note of these numbers. We now move on to the next example. This time, I have a linear operator pi from R3 to R3, do you remember this linear operator? It simply zeroes out the z coordinate. Okay, so for the kernel of pi, okay, the kernel will be points in R3 once again. So the point xyz is in the kernel if pi takes xyz to 0, 0, 0. But pi of xyz meant xy0, 0, 0, 0. And of course, this would mean x and y are both 0. Therefore, the kernel of pi consists of all points xyz where x and y are both 0. Hence, it consists of all points 0, 0, z, where z is a real number. But basically, you know that this set is simply the span of the vector 0, 0, 1. Okay? So therefore, a basis for the kernel is, what can you give as a basis for the kernel? The singleton containing the vector 0, 0, 1. On the other hand, for the range, the range or the image, we're looking at the set of all images, right, where x, y, z are real numbers over here. But pi of xyz consists of xy 0, where x and y are real numbers. Oh, I'm sorry. This 3 should not be there. Alright. And as you can see, the image, basically, the vector xy0, let me put it here. The vector xy0 can be written as a linear combination of 1, 0, 0 plus y times 0, 1, 0. So basically, this is the span of 1, 0, 0 and 0, 1, 0. I know that these vectors form a linearly independent set because one is not a multiple of another, right? So therefore, a basis for the image could be the set containing 1, 0, 0 and 0, 1, 0. Now in pictures, as you can see, so by the way, the nullity of pi is 1, while the rank of pi is also 2. In pictures or in geometry, if the kernel is generated by 0, 0, 1, we know that the kernel generated is actually the z-axis. So if this is your z-axis, this is your kernel. On the other hand, the range is going to be the entire xy plane. Alright? Why is that the case? Because it is the span of the vector 1, 0, 0. Ito yung 1, 0, 0. I'm sorry, let me change colors. So let's say this is the vector 1, 0, 0, and this is the vector 0, 1, 0. And this is the vector 0, 0, 1. The reason for this is because, remember, this mapping simply squishes the space into a plane. If you make the z coordinate 0, what happens is that every point in space will be taken down to the xy plane. Therefore, the image of this transformation is the entire xy plane. While, if you want to know the things that are mapped to 0, of course, they are all the points that are on the z-axis because they simply go down to the origin as you apply the transformation. Okay, so let's now move on to the next example. So this time I'm looking at the linear operator T on the space of 2 by 2 real matrices. Okay. This time the meaning of T, it is a transformation that transforms A to the sum of A and its transpose. for all A in M2R, right? So we would like to describe now the what they call this, the range and the kernel. So let's look at the kernel first. So the kernel of T consists of all the matrices. This time it's a linear operator, so always we will be considering the space M2R. So that T of A is 0. What is that? The 0 matrix, the 0 2 by 2 matrix. So here we're looking at the set of all A, so that A plus A transpose is the 0 matrix. So this is the space of all matrices, so that the transpose of A is equal to minus A. So as you can see, this equation is quite familiar, right? This is actually the space of all what? Of all what do you call this? Of all skew symmetric 2 by 2 matrices, right? So basically, this consists of all matrices of the form A, B, if A is a 2 by 2 skew symmetric matrix, we know that the diagonals are all 0. So if this is A, this is minus A, right? So that A is a real number. Hence, this is the span of the matrix 0, 1, minus 1, 0, right? So a basis for the kernel could be the set containing this matrix. And I know that the nullity of T is 1 because the basis only has one element here. Okay? On the other hand, for the image of T, we look at the set of all images where A is in M2R. But as you can see over here, you could write this as A plus A transpose, where A is a 2 by 2 matrix. So if you want to describe the elements of this, if you pick an arbitrary element of M2R like this and calculate A plus A transpose, how does it look like? It looks like, now if you add the transpose, that's 2A, 2D, this would be A, B, C, D, A, B, C, D, right? So this is going to be B plus C, B plus C. Alright? So as you can see, the resulting sum is nothing but a symmetric matrix, or an arbitrary symmetric matrix, because A, B, C, and D are arbitrary. No? We could also write the image of T as the set of all 2 by 2 symmetric matrices. And how do we represent them? It's of the form R, S, S, T, where R, S, and T are real numbers. And as you can see, a basis or the spanning set for this image consists of the matrices 1, 0, 0, 0, comma, 0, 1, 1, 0, comma, 0, 0, 0, 1. Because this matrix corresponds to the R, this matrix corresponds to the S, and this matrix corresponds to the T. It looks like that these matrices are linearly independent because one cannot generate one from the others. Okay? So therefore, a basis for the image consists of these matrices. Okay? 0, 1, 1, 0, 0, 0, 0, 1. Alright. And therefore, in this case, the rank of T is 3, which is the dimension of the image. Now, I gave these examples for you to observe something. Now, Now, when you look at the dimension of M2R, the dimension of M2R is 4 because you need 4 matrices to generate all of M2R at least, right? Because to determine a 2 by 2 matrix, you need 4 elements. Okay? So as you can see, if I add the nullity and the rank, 1 plus 3, it gave me 4. Here, the domain is 3-dimensional. The nullity is 1, the rank is 2, and 1 plus 2 is equal to 3. Also in the first example, the dimension of the domain is 3, the nullity is 1, the rank is 2, so therefore 1 plus 2 is equal to 3. So somehow, it seems like there's a connection between the dimensions of the kernel and the range or the image. In fact, that is what the next theorem is saying. The next theorem is what we call as the Rank-Nullity theorem. It tells us the connection between the kernel and the image of a linear transformation. That if the domain is finite dimensional, it follows that both the kernel and the image are finite dimensional as well, and their dimensions add up to the dimension of the domain. This is what we call as the rank-nullity theorem, as it says that the rank plus the nullity equals the dimension of the domain. So this is saying that once we know the size of the kernel, we already know the size of the range. Also, if one knows the size of the range, we already know the dimension or the size of the kernel. Okay? Alright, so let us have the proof of the following. So here we're assuming V is n-dimensional, so that it's finite dimensional. Okay? Because the kernel of L is a subspace of V, then V cannot have, then the kernel cannot have a dimension more than n. So in fact, the thing that we are sure is that the kernel is also finite dimensional. So let us say that the kernel has a dimension R where R is less than or equal to n. In this case, I took a basis for the kernel with R elements in it, V1 up to VR. Because this is a basis, this is linearly independent in V, we know that linearly independent sets can always be extended to be a basis for the mother space. So in this case, I'm going to extend this. So by this, now this is what we're doing. So we are having this vector space V. So let's try to draw a picture representing the proof. Okay. So over here, here is the kernel. The kernel has a basis consisting of R elements. Okay. But because V is n-dimensional, we can extend this basis to be a basis for the entire V. So there's an addition here, VR plus 1, VR plus 2, up until you reach n vectors that can generate all of V. So only V1 up to VR are sure to be in the kernel. This extension should be outside the kernel, right? Okay. Let's go back. We claim now that, so this is what we're going to do. Take note that because these vectors are in the kernel, so this is the 0 of the W, everything in this kernel, actually this entire kernel gets mapped to the 0 vector of W. But because these vectors are not in the kernel, they will move to somewhere else aside from 0. So for example, this could be the image of VR plus 1. This could be the image of VR plus 2. We don't know where, but this is just a representation. This is the image of Vn. Alright? What we claim here in the proof is that we wanted to prove that this collection, this will form a basis for the image. Okay? That's what we want to prove. So if this is your image, yeah, we wanted to prove that these vectors form a basis for the image. So let's go back to the proof. Yeah. Okay, so let's prove that this is a basis for the image. By the way, how many elements are there in the kernel? In the basis for the kernel, we have R vectors over here, right? How many elements are there in B double star? In B double star, there are n minus r. Why n minus r? Because we simply have removed, this was taken from this set with n vectors, right? You just have removed this. Okay, so if this forms a basis for the image, then there are n minus r. So if you now go to add, if you now going to add, you are now going to add the dimensions of the kernel and the image, get r plus n minus r, which is equal to n, and which is the dimension of v. So we're done. So that's why we wanted to prove that this set forms a basis for the image. To prove that this is a basis, we prove that it spans the image. Second, it's linearly independent. So we first prove that it spans the image by taking an arbitrary element in the image. Let's say W. I need to prove that W is just a linear combination of this. But because W is in the image, I know that something in V, must go to W because that is the range. Now there is some V in the domain which are mapped to W because it's in the image. And because V is in V, V is generated by this, V is generated by this basis B star, okay? Then I can write V as a linear combination of the VI's, I from 1 up to n, like so. The scalars are AI, so I'm just writing the sum in summation form or in a more compact form, okay? You could always expand if you want. If I now take, or if I now apply L on both sides, you get L over here, L over here. This L of V equals W, right? But the L of this sum is the sum of the L's, if you can remember. L of the linear combination is the linear combination of the L's. So it becomes like this sum. What happens is that if we're going to expand this equation, it becomes like this. Let me show you. W happen to be the sum AI L VI I from 1 up to n. So if you're going to expand A1 L V1 plus blah 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 AR L VR plus AR plus 1 L VR plus 1 up to AN L VN. But as you can see, the V1, this vectors V1 up to VR is a basis for the kernel. Therefore, they are in itself in the kernel. So if they are in the kernel, these vectors will be simply mapped to 0 in W. So all of these guys are 0. So 0, 0 up to there. So what we are left is that W is nothing but a sum of AI L of VI I from R plus 1 to n. So that's what happened here. This is the only thing that will be left from R plus 1 up to n. Therefore, because B double star consists of these vectors, that proves that W is a linear combination of this. Therefore, what? B double star spans the image. To finish the proof, we also only need to show that B double star is also linearly independent. Now suppose that the sum AI LVI I from r plus 1 to n is 0. We need to show that these scalars are all 0, but that's not hard to show. First, simply take note that this, because L is linear, this equation translates, or you can move this L outside the sum, right? This translates to this equation. And this would mean that this sum is sent to the 0, or it's being killed by L. Therefore, that sum is in the kernel. But if this is in the kernel, we know that the kernel is generated by B, right? Or B is a basis for the kernel kasi. Therefore, this sum itself is a linear combination of the elements in B. But what are the elements of B? The elements of B has V1 up to VR in it. Therefore, I can write this sum as a linear combination of the VI's I from 1 to R. So there are scalars B1 up to BR, so that this is equal to this. But if you're going to put everything on the left, so we have the following equation. If I'm going to expand this sum, this is nothing but B1 V1 up to BR VR. And then I have minus AR plus 1 VR plus 1 minus AR plus 2 VR plus 2 and so on, minus AN VN equals 0. But because this extension V1 V2 up to VR up to VN is a basis for V, that's the extended V, right? Because this is a basis for, that's actually the B star, V1 up to Vn. This is a basis for V, therefore linearly independent. So whenever you have this linear combination equal to 0, what's the conclusion? All the scalars are equal to 0. In particular, these AI's are 0, I from R plus 1 to N, which proves that this sets L of VI, the B double star, is linearly independent, therefore a basis for the image. Finally, the dimension of the kernel plus the dimension of the image equals R plus N minus R, which is N, which is equal to the dimension of V, finishing the proof of the Rank-Nullity theorem. How about the kernel and range of a matrix transformation? Remember that if you have an m by n matrix, it gives us a linear transformation called as a matrix transformation. This matrix transformation associated to an m by n matrix A, remember, it's a transformation from the n-dimensional Fn to the m-dimensional Fm. How do we get these things done? You take a column vector from Fn, right? You send it to A times X because this is m by n. This is n by 1. So the resulting product is m by 1. So this is an Fm. That's how we perform TA of X. No? We simply multiply A on the left. If you look at the kernel of TA, it consists of all points in the n-dimensional Fn which are mapped to 0. In other words, when you multiply A on the left, you get 0. Therefore, if you look at this, this is precisely an m by n homogeneous linear system. Therefore, the kernel of the linear system simply is the solution set of the homogeneous linear system AX equals 0. So you are going to simply solve for the solution space of this homogeneous linear system. And this solution space is what we call as the null space of the matrix A. So for a matrix transformation, TA, the kernel is nothing but the null space of A. Now, the null space of A consists of all the solutions to the linear system AX equals 0. How about the image? So the image consists of all the images or the products A times X, where X is an n by 1 column vector. The question is, what are the elements of this image? Of course, we know that the elements are the products of the form AX, but of course, it's not possible to get all the products AX for X in Fn, because as this set is always infinite, right? Oftentimes infinite. So what we do to describe the elements is we look at, or we give coordinates, or we give entries to A. So let's say A has Aij in it. And let's say X is a column vector. So I just written it in row form to save space. So let's say X is the column vector x1 up to xn. That's why there's a transpose over there. I'm going to look at AX. So this is AX. Yeah. When you multiply that, you get this familiar thing. But take note that I could actually separate this vector into vectors of this form plus vector of this form plus vector of this form, right? I could do that. And then I can factor the x1 over here, factor the x2 over here, factor the xn over here. So I get the following. Therefore, as you can see, AX is precisely a linear combination of the columns of A. So, if you want to know all the set of all AX, you may want to know the set of all linear combinations of the columns of A, or the span of the column. Therefore, the image of TA is the span of the columns of A, known in linear algebra as the column space of A, denoted by C of A. Okay? So in terms of matrix transformation, the kernel is the null space. Simply solve AX equals 0. The column space is the span. I'm sorry, the range of TA is the column space of A, which is just the span of the columns of A. You simply take the linear combinations of the column. With this, whatever the dimension of the null space is, that is also called as the nullity of the matrix. The dimension of the column space will be called the rank of the matrix A. Okay? And by the rank-nullity theorem, the rank of a matrix plus the nullity of a matrix is equal to n, which is the number of columns. Okay? So let us illustrate this in the following example. So here we're going to find bases for the null space and column space of the matrix. Now in this exercise, all you need to do is to find the RREF of A. Mind you, the RREF will tell you all the things that we need here. Okay? So I'm going to teach you the steps. So first, you just take the RREF of A. So I think this time, because the matrix is big, let's kind of use the GeoGebra to perform the RREF for us, right? So let me switch to the GeoGebra screen. So there is the GeoGebra screen. So I'm going to now put the matrix A over here. So A is defined as, the first row is -3, 6, -1, 1, -7. The second row being 1, -2, 2, 3, 3, -1. The last row being 2, -4, 5, 8, and -4. So that's the matrix A, right? Is that correct? Did I copy it correctly? Yes. So let's now perform. You just type reduced row echelon form. Hit A and then enter. So this is the reduced row echelon form. Let me write it for you. And right, 0, 1, 0. Yeah. So as you will see, you will think the Gauss Jordan for this. Okay, so let me switch back to the slide view. Alright. There. So, in order to know the null space of A, you just solve for the vectors x so that ax is equal to 0, right? So, when you solve for ax equal to 0, you just put a 0 column over here, right? But if you perform RREF, that just remains a 0 column all throughout. So you just don't need to worry. So the null space of A now consists. So if you label the variables as x1, x2, x3, x4, x5, if you want to call it like that, because there are more than 3, so it might be difficult to use x, y, z. Okay, so the null space sorry. So the vector x1, x2, x3, x4, x5 is in the null space if and only if it satisfies this linear system. So here the free variables, so we only have 2 pivots right over there. Therefore, there are only 2 leading variables, x1 and x3. All the other 3 variables are free. So, for example, if x2, the free variable is named r, x4 is named s, and x5 is named t, if you want to call it like that, using the first equation, how do you solve for x1? x1 is, you're going to put this on the right? So it's going to be 2x2 plus x4 minus 3x5. So this element is going to be 2x2, which is r, plus s minus 3t. Okay? For x3, you look at the second row. You look at this. x3 is now, you put this 2 on the right, minus 2 x4 plus 2 x5. So that's minus 2s plus 2t. So there. I was able to write the solution set easily. So what I do now is I'm just going to write this as a linear combination using the constants r, s, and t. So for r, we have 2, 0, 1, 0, 0. Oh my gosh. Yeah. What happened here? Why do I have a lot of... Oh, okay. So this is a plus. So that's where I missed. So that's 2, 1, 0, 0 plus s times 1, here walang s, here minus 2, and then 1, and then 0. For t, you have minus 3, 0, 2, 0, 1. Right? So therefore, as you can see, every element in the null space is nothing but a linear combination of these 3. Okay? So therefore, the null space of A consists of, or is the span of the vectors 2, 1, 0, 0, comma, 1, 0, minus 2, 1, 0, comma, minus 3, 0, 2, 0, 1. So when I ask for a basis for the null space, you give me a set. You just write these vectors down here. I don't have to. Why do I know that this is a basis? Because this is linearly independent already. Look at this. This doesn't look like a multiple of this. because this is 0. I'm sorry, this is, yeah, this is 1, that's 0, right? Oh my gosh, I think I missed something. Why does this only have 4 coordinates? 2, 1, 0. Oh, one more 0. Okay. All right. So that's the null space. This is the kernel of the matrix transformation. It's three-dimensional. Now, how do we get for the image? The image will be the column space of the matrix. Okay? For the column space, you simply get the span of the column. So you take the columns over here, 1, 3, 1, minus 3, 1, 2, 6 minus 2, minus 4. The second column, third column is this. Fourth column is 1, 3, 8. And that's minus 7, minus 1, minus 4. Ayan. Now, because, you see, the range of this matrix transformation is in R3, so the maximum dimension is 3. So definitely one of these, at least two of these vectors are redundant. How would you know? We have already talked about this one. To know which ones are redundant, you place them again in columns, run the RREF. You look for the columns with no pivots. They are redundant and they can be erased. So in this case, only the first and the third column has a pivot. Therefore, the second vector and the last two are redundant. So therefore, the column is what? Will now only have minus 3, 1, 2, and minus 1, 2, 5 in it. And this will form a basis for the column space. So in this case, what can you say about the nullity of A? The nullity of A is 3. It was generated by 3 vectors. And the rank of A, which is the dimension of the column space, is 2. And as you can see, once again, 3 plus 2 is equal to 5. And 5 is the number of columns, which corresponds to the dimension of the domain. Okay? So, what did we notice over here? The rank is basically just the number of elements in a basis for the column space. Therefore, it's just the number of pivots. And the null space, because of the rank-nullity theorem, it's just going to be the number of free variables, because this will determine, right? That will determine how many vectors will span the null space. In general, if you have an m by n matrix, this is m by n. I'm sorry, this is m by n. Okay. The rank of A is simply just the number of pivots in the RREF of A, or the number of leading variables if you want to look at it as a linear system. On the other hand, the nullity of A is nothing but the number of columns in the RREF of A without a pivot, or if you want to view it as a linear system, it's the number of free variables. Okay? In the next video lesson, we shall reveal why this kernel and the range or image is important in determining how the linear transformation behaves as a linear transformation. Alright? So, see you in the next video lesson.